And we have Guy back with the second part of safety in AI systems. So it's all yours.
Okay, thank you. So welcome back, everyone. If anybody missed yesterday's talk, so my name is Guy Katz. I'm from the Hebrew University in Jerusalem, and I will tell you a little bit about verifying neural networks, so systems with neural network components, machine learning components. So I'll start with a very brief recap of what we saw yesterday, just so that we remember where we stopped. So let me just jump to the verification problem. This is all stuff that we saw yesterday. Right. Sorry. Yeah. Okay. So this is what I was looking for. So remember that we saw yesterday that we have a situation where we want to use deep neural networks, and they're used as a black box, right? We have them automatically trained, and we're not sure how they operate. And then we saw that there can be various kinds of problems with these artifacts. For example, we saw adversarial examples where you take a neural network and you slightly perturb its input, and suddenly you get a wrong answer. We also saw examples from the AKSXU domain, where you have a system that does airborne collision avoidance, and you want to be sure that it doesn't issue any false advisories, etc. And we saw a bunch of these examples, and we said that they are all reducible to one simple, or well, not so simple, but simply defined problem that we want to solve. And that is the neural network verification problem that we see here. So we said that for a neural network N that maps a set of inputs into a set of outputs, and given an input property P that characterizes the inputs that we are concerned with, and an output property Q that characterizes the bad behaviors that we want to avoid, the verification problem is to decide whether there exists a concrete input, X0, that satisfies P and gets mapped to an output Y0 that satisfies Q. And so this is the basic problem that we want to solve, and all of the problems that we mentioned are all reducible into this setting. Right, so we said that P characterizes the inputs that we care about, and Q characterizes the undesired output, so the outputs that we want to avoid. If we get a negative answer, which we call unsat, meaning that these constraints are not satisfiable, then we know that the bad behavior characterized by Q cannot be obtained. So we know that everything is good and we are happy. Otherwise, if we get a SAT answer, then we have a counterexample. We have a concrete input for which the property is violated, and so we have a counterexample that we can return to the user. So this is the verification problem as we defined it. And then we proved that even for a simple neural network that only has ReLU activation functions, and even for very simple input and output properties, namely conjunctions of linear constraints, the verification problem is NP-complete. It's NP-complete in the number of the ReLU nodes in your network. So the larger your network, the worse the verification complexity will become, exponentially so. Right? So it will become very, very tricky to verify large networks. So this was what we said yesterday, and we even proved this claim. Well, almost proved it. I left one small hole in the proof, but hopefully you were convinced. And then what we did was we discussed some of the techniques and challenges in verification, and we talked about complete techniques. Right, so let me jump to that slide. So we said that for any ReLU constraint that we have, we can regard it as a disjunction of two linear constraints. Right, so remember, the y equals ReLU function returns the identity function if x is positive and 0 if it's negative. So we said that each such ReLU constraint can be regarded as a disjunction of two linear constraints. One is the linear constraint for the active phase that reads x is non-negative and y equals x. So this is the identity function. And the inactive phase that says that x is negative and y is 0. Right, so we have a disjunction between these two linear possibilities. And then we said that one sound and complete algorithm that you can solve for, that you can apply for solving the verification problem is, let's see, it's this case splitting approach. Right, so it says, take each of your ReLU constraints, guess whether it's active or inactive. Once you have guessed for all of your ReLU constraints, you get a linear problem. It's only a collection of linear constraints that you are left with. These you can solve using a linear programming solver, and there are mature tools that you can use for this purpose. If a solution is found for your guess, you return SAT and you stop. You have a counterexample, you're happy. But if the problem that you solved is unsat, if there is no solution, then you don't know, is it because I made an incorrect guess or because there really is no solution? And then you need to try another guess and continue until you have exhausted all of your possible guesses. And because the number of guesses is exponential, in the worst case, you get an exponential runtime for this algorithm. And this is very similar to the Boolean satisfiability problem where you need to guess for each input variable whether it's true or false. So this is what we said yesterday. Are there any questions or comments on that before we continue to the new stuff? And again, feel free to use the chat window if you prefer. No, okay. So let's jump to where we left off yesterday. Right, so this is where we stopped. So in the first half of today's lecture, I will present the ReLUplex algorithm, which is one of these complete verification algorithms that I mentioned. Only it has some very interesting enhancements to the basic complete approach that we saw that traverses the entire search tree. Intuitively, even for very small networks, right, that only have a few hundred neurons, if you wanted to traverse the entire search tree, you wouldn't be able to do so in a reasonable amount of time. 2 to the power of 200, 2 to the power of 300 operations is already more than your laptop computer can do. So in ReLUplex, which is an algorithm that we published in 2017, we proposed some enhancements that allowed you to traverse these search trees more efficiently. And this is what I want to show to you now. So this we said yesterday. So this is a collaboration with these 4 researchers. And okay, so let's repeat this slide. So we said that basically what ReLUplex is an SMT solver, which I won't elaborate on. I don't want to go into what SMT solvers are, but intuitively these are tools to which you give a set of constraints and they answer SAT or unsat. And this particular SMT solver is very useful for quantifier-free linear real arithmetic plus ReLUs, which is precisely what you need in order to encode a neural network, as we will see. It's based on the simplex method for solving linear programs. So simplex is a very well-known algorithm that only solves linear constraints, and we extended it to also handle these ReLU constraints, and this is where the name comes from. It's simplex plus ReLUs, you get ReLUplex. Okay, and the key SMT idea that we take and apply here is the laziness. Right? So laziness means that when you traverse the search tree, instead of jumping directly to a leaf and trying to see whether it's SAT or unsat, and then you have to explore exponentially many leaves, instead of doing that, you stop at the middle of the search tree and you try to solve the problem at the intermediate nodes. And this you can do hopefully very efficiently. You have to traverse a much smaller portion of the search tree. So sometimes you still have to split, right? There's no way to avoid case splitting at all to guess for a ReLU whether it's active or inactive. But if you do this lazily, then often you only need to split on a small fraction of your ReLUs. So this is what we will show. But before we can talk about ReLUplex, we need to talk about simplex. So simplex is, like I said, a very famous algorithm. It was developed by George Danzig, whose picture you see here. And it's an algorithm for solving linear programs, right? So I remind you, linear programs are a collection of linear equations and variable bounds, and sometimes also an objective function, although we will not concern ourselves with objective functions in this talk. And this algorithm, although it's very ancient, right, it's been around for a very long time, it's still very efficient. And even in modern solvers for linear programming, you see that they still implement versions of simplex. So typically simplex is divided into 2 steps. In the first step, you find a feasible solution. So remember, simplex has a set of equations and constraints that specify which are the feasible assignments to your variables. So the first thing that you do is you just find a single assignment that is feasible, that satisfies all of your constraints on the input region. And then once you have this first feasible solution, you optimize it. Right? So you also have an objective function. And once you have this feasible solution, you start optimizing it according to the objective function until you find the optimal solution. So these are the 2 steps of simplex. And this is a very well-known terminology. You talk about simplex phase 1, simplex phase 2. These are the 2 phases. But for us, because we care about feasibility, we care about satisfiability, right? We need to know unsat or sat, then we don't care about optimization. We only care about finding a feasible solution or determining that such a solution does not exist. So we will focus only on phase 1. Now, yesterday, somebody asked about using these tools to optimize. right? Not just to solve decidability questions, but also to optimize some objective with regards to an objective function. So yes, you can also do that. If you want, I can send you a manuscript. So if anybody's interested, send me an email and I will reply with a link. But in these series of talks, we will not concern ourselves with optimization. So how does simplex work? So it's an iterative algorithm. It always maintains a variable assignment. We will see an example soon. But remember, we had a set of variables for which we needed to find an assignment. So we always maintain a variable assignment. And we will make sure that our assignment always satisfies the equations that we were given. But it may temporarily violate variable bounds. Right? So we might have a constraint that says that y needs to be smaller than 5. And currently in our assignment, y equals 7. This is fine. We allow this. But simplex will try to iteratively fix any such violation. Right? So it will take y if it's currently too great, and it will try to reduce it to be within its bounds while still maintaining the equations. So the terminology of simplex, which will become clearer when we see an example very shortly. So the variables that we have in our problem are divided into basic and non-basic variables. And so this is common simplex terminology. Intuitively, the non-basics are the free variables. These are variables that you can change freely. You can assign them values without worrying too much. And the basic variables are the bounded variables. So once you have assigned values to all of your non-basic variables, these determine the values of the basic variables. So really, the non-basic assignment is what dictates the assignment for the basic variables. And in every iteration, simplex will do one of two things, or both. It can update an assignment of a non-basic variable. Remember, we said non-basic variables we can change freely, so we can update the assignment of one of these, and consequently also update any basic variables that were affected. Or we can do a pivot step in which we switch a basic and a non-basic variable. So these are the two operations that simplex uses in order to solve the system of constraints or decide that they cannot be solved. So now let's see an example, which I hope will clarify things. So suppose we have this very small neural network. Now, this is our toy example. So it has a single input neuron, 2 hidden neurons, and a single output neuron. And suppose for this part of the slides that there are no activation functions. Okay, so no ReLUs, no maxes, nothing, just the weighted sums that you see. Remember, we said that simplex is good for solving linear constraints. It's not so good for solving ReLUs. So in order to demonstrate simplex, we will ignore the ReLUs temporarily. And remember that we need to check a property. So the property that we are after is we're looking for x1 that is between 0 and 1, and x4 that is not between 1/2 and 1. And so this is the property that we want. I'm sorry, and we want to prove that x4 is always not in this region. So as usual, we will negate our property, and what we will really look for is the counterexample. So we will look for an x1 that is between 0 and 1, and x4 that is between 1/2 and 1. Okay, so this is the problem that we want to solve. This is the verification problem. So we have the neural network, we have the input constraint and the output constraint. So the first thing that we do is we translate the neural network into a linear program. All right, so remember, in a linear program, we are allowed to have equations. So we will have an equation for each weighted sum in the neural network. So for example, if x2 equals x1, right, it's the weighted sum for x2, then we will have the equation x2 minus x1 equals 0. If x3 is minus x1, we will have the second equation. And if x4 is the sum x2 plus x3, we have the third equation. So each weighted sum is directly translated into a single equation. This is pretty straightforward. Then come the bounds. This is the other thing that we can have in a linear program. So x1, we know that its bounds are given to us by the property. It's between 0 and 1. x4, again, given by the property between 1/2 and 1. And x2 and x3, we don't care. They can be unbounded. Their values are not restricted in our verification query, so they can change. And observe that now, once we have this, so what we have here is a linear program. Okay, it doesn't have an objective function, but that's fine. You don't need to have an objective function. So this is a linear program, and it completely corresponds to the verification problem. Right? If you are able to find a satisfying assignment here, then you have a counterexample. If you cannot solve this, then there is no counterexample. Right, so this is a complete equivalence. Now, simplex has this technical issue. It doesn't really like these zero constants that are floating around. So simplex really prefers that we introduce auxiliary variables. So we're going to remove these three zero constants, and we're going to replace them with fresh variables, x5, x6, and x7. We call them the auxiliary variables, and we're going to require that they are precisely zero. So this is a purely technical step. It doesn't change anything about the satisfiability of the problem. Right? You just replace them with these auxiliary variables. Any questions on this encoding or anything that I've said so far? Okay. So now comes simplex, right? So we said simplex, do we really need to use the three variables for three zeros? So yes, okay. So we need three variables because, as you will see very shortly, we need to have three equations, and these are going to be our basic variables. So yes, one variable for each equation. Now, in our example, they were zeros, but in a real neural network, you can also have bias values. So you might have constants here that are not zeros, and then you could have a different constant for each equation, and then you would definitely need a fresh variable for each one.
Is there any difference between introducing these auxiliaries and just saying, as an example, the last equation, x4, rather, it would be x2 plus x3 equals x4.
You could also do that. It doesn't really matter, but you could do that trick also. Okay. So now let's see how simplex solves this problem. Okay, so actually, before we see how simplex solves it, I forgot to ask you, is there a solution to this problem, right? So if you intuitively look at this neural network, because there are no values, you will see that no matter what you assign to x1, x2 will be equal to x1, x3 will be minus x1, and then x4 will be x1 minus x1. So it will always be 0, right? So there will be no way to satisfy the constraint that x4 is between 1/2 and 1. So we expect simplex to say that there is no solution to this problem, right? But now let's see how simplex does it. So simplex, remember, is an iterative algorithm, right? So it has a state and it iteratively adjusts the state. So this is the state, what you see here on the screen. So the state contains the equations. So we have the three equations from before. And we have this table that shows us the variables that we have, the current assignment for each variable, the lower variable bounds and the upper variable bounds. And so some variables are bounded. For example, x1 is between 0 and 1. The other variables are unbounded. So x2 and x3 don't have bounds in this table. That's fine. And the starting assignment is 0 to all the variables, and this trivially satisfies the equations, right? If you assign 0 to all of your variables, then certainly your equations hold. And now simplex starts to iteratively try to solve the problem, right? So currently we have an issue with x4. x4 should be at least 1/2, but it's currently 0. So we have an issue here and we need to try and address it. So now simplex starts. In the first iteration, it marks x4 as a problematic variable that needs to be corrected. And what does correcting here mean? So x4 needs to be at least 1/2. It's currently 0. So no problem. Let's do an update step. Let's increase x4 from 0 to 5. To 1/2, sorry. So remember, we said that we can only do this trick for non-basic variables, but this is fine because the variables that you see on the right-hand side of the equations are non-basic. These are variables that you can play with freely. And the variables that you have on the left-hand side, these are the basic variables. So these values are determined by the values of the non-basics. So x4 is a right-hand side variable. It's non-basic. We can just update its value. So x4 is increased to 1/2. But because we want to always maintain the equations, if we touch x4, we also need to touch x7. So x4 is increased, and likewise x7 is also increased. So both of them become 1/2. And when the first iteration is done, x4 is good, right? It's no longer problematic. It's now within its bounds. We're happy, and the equations always hold. So no problem there either. But now in the second iteration, we have an issue with x7, right? It should be at most 0, but it's currently 1/2. That's not good. So in the second iteration, we target x7. Now with x7, we can't do the update trick again because x7 is a left-hand side variable. Right? You can't just change its assignment. You cannot do this because it's determined by the non-basic variables. So what must you do before you can change x7? Well, easy. You need to pivot. What does pivot mean? It says take x7, which is basic, pick another variable that's non-basic in its equation, for example, x2, and just do an arithmetic manipulation that will switch them. So this is the original equation, and it becomes this equation. X2 and X7 simply switch places. So once we do this, X7, oops, I'm sorry, this is the new equation. Right, so we're going to replace this equation with the equation on the right. So once we do this, X7 will become right-hand side variable. It will become non-basic, and then we can update it. Now, we don't allow variables to be both basic and non-basic at the same time. Right? So you cannot move X2 to be basic and then leave it non-basic in this equation. So we need to eliminate X2 from this equation as well. So instead of X2, we substitute it with this equation here. This is completely technical. It's a very simple arithmetic manipulation. And once we are done, we get these equations in which X2 is indeed basic and X7 is indeed non-basic. So this is the pivot step. And after we do that, now X7 is non-basic and there's no problem. You can just update its value. You decrease it back to 1, 0, to be 0. So X7 is decreased. And because X7 affects X5 and X2, both of them need to increase. Right? X7 appears with a negative sign. So if you decrease its value, X5 and X2 will increase. So this is what happens after the second iteration. Okay, and indeed, after this iteration, X7 is good. We continue a little while longer. So now X5 is too great. It's a basic variable, so we need to do a pivot. It's more of the same, so I will rush through this. And then you can update X5 to be 0, which is good. And then in the final step, you look at X6 and you say, X6 is too great. It should be 0, it's 1/2, that's not good. And it's a basic variable, right? So we cannot just update it, but we need it to decrease. And at this point, simplex will actually say failure. And how does this failure come about? Well, X6, if you look at the equation, equals to X4 minus X7 minus X5. If you want X6 to decrease, then X4 would need to decrease. But we have a problem, right? X4 is already pressed against its lower bound. It cannot decrease any further. So no luck with X4. Alternatively, you could have X5 or X7 increase because they appear with a negative sign. But no luck here either, because X5 is pressed against its upper bound, and so is X7. So in other words, this means that X6 is at a minimum. Right? It can never go down below 1/2 because of this equation. And consequently, it can never be less than 0, and consequently, the problem is unsat and you get failure. Right, so this is not surprising to us because we knew that the verification problem is unsat in this particular instance. But this is how simplex comes to this conclusion. Any questions on simplex?
Is there a restriction on a variable once it becomes non-basic that you can't pivot back?
No, that's not an issue. You can pivot back and forth. That's fine.
Okay. And second, how do you pick? Because in the first step, you picked the magical value of exactly 0.5.
Ah, okay. Oh, I thought you were on to me, but you're not. That's good. So I will tell you what I mean. But at the first step, right, when we started,
Yeah,
so simplex will always, I'm sorry, X4 you mean?
Yeah.
All right, so we just needed it to meet its lower bound, right? So it was too small, so we increased it up to its lower bound. So this is pretty standard practice. If a variable is too small, you increase it to its lower bound, and if it's too great, you decrease it to its upper bound.
Okay. And if if you have a choice of updates, because here you could have increased by anywhere between 0.5 and 1.
Right. So there are some. So you're correct, right? You could do that. I don't think this is done in practice. It's not a limitation of the algorithm. You could do it. I'm not aware of any implementations that choose to do that. The degree of freedom that is more interesting, which I thought you were asking about at first, is how do I pick which variable to pivot? Right. So when I said that I need X7 to be non-basic, and I just said, well, I'm going to pivot it with X2, but I could just as well pivot it with X4 or X3. Right. In this case, definitely X3 would also be a good candidate. So this part is where heuristics come into play, and there are many heuristics that folks have developed over the years for which variable to pivot with. And we know that this is very crucial for performance of simplex.
And do they sort of like circle around the idea of finding a variable that occurs in smaller right-hand expressions?
So there are some heuristics that do that, but the more clever heuristics try to assess which variable will be the best pivot in the sense that it will reduce the overall infeasibility of the problem.
Okay.
Okay, this is really complicated stuff that is beyond the scope of this talk. But yeah, this is a good point, and we know that performance of simplex really depends crucially on these things. So it's a very important question. Okay. So some properties of simplex, right? So I didn't precisely define the algorithm to you. I just showed you an example, but I hope it conveyed the core essence. But we know we can prove that the simplex algorithm is sound. So if it says sat, the problem is sat. If it says unsat, the problem is unsat, and complete with a little star. So what does this star mean? Well, the algorithm is complete, but it could run into circles if you're not careful, right? So you could theoretically pivot a variable and then pivot back, and then pivot again, and then pivot back, and run in a circle without ever terminating. So in order to guarantee that this cycling doesn't occur, you need to be very careful about the way that you select which variables to pivot with. And there is a famous strategy for pivoting called Bland's rule, named after Bland, who invented it. And we know that if you use this strategy or one that is similar, then you are guaranteed that the algorithm will terminate. And so you need to be careful. If you're careful about variable selection, you will terminate. These strategies are often slow. So people prefer in practice to use other strategies that don't guarantee termination, but are faster in practice. But theoretically, we know how to ensure that the algorithm will terminate.
Somebody asked in the chat if there's a complexity bound for simplex, and that
excellent
probably apply
question.
to
An excellent question. So this is precisely my last bullet here. So the linear programming problem is known to be in P, right? So it's solvable in polynomial time. It's actually unknown whether simplex is in P or not. Okay, so it's an open question. Can you find a variable selection strategy for simplex that makes it run in polynomial time? For all the variable selection strategies that we know of, there is a situation where the algorithm will run exponentially, but in practice, it's still very, very fast. So this is a really funny story, right? You would expect an algorithm that is formally in P to run faster than an algorithm that is probably only in NP, but in practice, this algorithm is much faster than algorithms that are guaranteed to terminate in polynomial time. So this fits very nicely with the overall approach in verification, where we know that the problems are very difficult in theory, but in practice you can solve them. Right? So in theory, simplex is probably, it's an open question, but it's probably in NP, but still in practice it runs very quickly. So if you can prove that simplex is either in P or not, then you will have eternal glory. Okay, so that's about simplex, right? So like I said, a very well-established algorithm. But now, what do you do about ReLUs? Right, so what we propose to do in ReLUplex is to take each variable that represents a ReLU. So now the ReLUs are back, right? Now we have the activation functions in our neural network, and we will each ReLU represent using two variables. One to represent the weighted sum that's going into the ReLU, the input, and one to represent the activation value that's coming out of the ReLU. So the weighted sum and the activation result. And we will use the W and A superscripts to distinguish between the two. And now we're going to let these two variables change independently. And this is one of the crucial points of the algorithm. So we know that there is a ReLU constraint, but we're not going to enforce that the input and the output satisfy it. We're going to let these two variables change independently. They may temporarily violate ReLU constraints, very similar to how simplex allows variables to temporarily violate their bound constraints. And we're going to incrementally fix any such violations until we converge to an answer. And just like simplex, we will use pivots and updates. Okay, so same operations as before, only now we will use them also to solve any ReLU violations. So this is the same neural network from before, only now we have the ReLU constraints applied to x2 and x3. So they have activation functions, they have the ReLUs. So the picture changes into this one, where the inputs and the outputs to the ReLUs are separated into two distinguished variables. And so x2w and x2a together signify the original ReLU, and x3w and x3a likewise match this ReLU here. So now, once we have this representation of the problem, we again introduce equations. Okay, so for each weighted sum, we have an equation, same as before, only now we have the W superscripts and the A superscripts where appropriate. So same strategy as before. And the bounds are also very similar. Okay, so x1 and x4 are given to us by the property that we're checking. The weighted sum variables, they are unbounded. They can be whatever they want. The activation result variables, because ReLU's outputs are non-negative, we allow ourselves to restrict them to be between 0 and infinity. And the auxiliary variables, as before, are zeros. So if before we had an exact translation from a neural network into equations and bounds, now we have equations, bounds, and also the ReLU constraints. We need to remember that x2w and x2a are connected, right? And this is represented by the fact that they share an index. So now how does ReLUplex run? So very similar to simplex, right? We have the state, and the state is comprised of this table that shows us the current assignment and bounds and the equations. And we start much like we did before. First iteration, we look for any violations, and we see that again, x4 is too small. No problem, it's a non-basic variable, we can update its value. So we update it to be 1/2. It meets its lower bound. And because we always maintain the equations, if you touch x4, you need to touch also x7. So both of these variables change to 1/2. First iteration is done. As before, x7 is now too great. We need to reduce its value. No problem, it's a basic variable, so we first do a pivot. All right, so we switch between x7 and x2a, very similar to what we did before. And after this pivot is done, x7 is now non-basic, and we can update its value to be 0. So the value of x7 decreases, the value of x2a increases because of this equation that connects the two of them. And now comes the divergence from simplex. So at this point, after the second iteration is done, all of our variables are between their bounds. Nobody is too small, nobody is too great. And all of the equations hold. The only problem is now a ReLU constraint. So x2w, the input to the second ReLU, is 0, but the output is 1/2. And this doesn't make any sense with the ReLU definition, right? You can't have this situation. So what do we do? The same thing that we always do. We update a value. And so we take x2w and we say, look, you shouldn't be a 0, you should be 1/2. So we update its value to be 1/2. And we are allowed to do this because it's a non-basic variable. And so the value of x2w will be increased. We always maintain the equations. So if we touch x2w, we touch x5 as well. So both of them change, and the assignment becomes 1/2. And when this step is done, this ReLU is now satisfied. Okay, the input is 1/2, the output is 1/2, and that's great. This ReLU is active and satisfied. And a crucial observation is that we didn't do a k-split. Okay, we didn't guess in advance that the ReLU was either going to be active or inactive, but instead we started to solve the problem, and we on the fly determined that it's a good idea to have this ReLU active. But because we didn't do a split, we didn't incur the big search tree, right? We're not reversing the search tree because we didn't need to do a split on this ReLU. This is the laziness. This is what it means to try and solve the problem at the intermediate nodes of the search tree instead of jumping straight to the leaves. So after this iteration is done, x5 is now too great. It should be at most 0, but it's 1/2. So we do some more simplex steps. It's more of the same, so I will skip. And so some pivots and some updates, and it continues until at some point, simplex stops and it says, ReLUplex stops and it says success. Why success? Because all the variables are between their bounds. Nobody is too small, nobody is too great. The equations we know always hold because we always make sure that they hold. This ReLU is active and satisfied. The input is 1/2, the output is 1/2, that's great. And this ReLU is also satisfied. The input is negative, the output is 0. And so one ReLU is active, one ReLU is inactive, but that's fine. Both of them are satisfied. And so simplex ReLUplex no longer has anything that needs fixing, so it says success, it's happy. Right, and indeed, if you take the original neural network that we started from and you place the values that ReLUplex found, you see that this is indeed a satisfying assignment that satisfies the property that we were after. Okay, so this was impossible to do when we didn't have activation functions, but it's quite possible when you have ReLUs. And because this ReLU here zeroes out the minus 1/2, and so you get 1/2 at the output, which is what you needed. So I, of course, didn't formally define the algorithm. Right? I didn't even show you pseudocode. I just gave you an example, and I hope it conveys the core principles of the algorithm. Of course, you are more than welcome to look at the paper and read the full definition. Are there any questions on ReLUplex?
Is there any sort of ordering to the operations? Do you sort of go from the output towards the input, even as a guide, if not like as a hard rule, to sort of make it look like backpropagation?
So we experimented. So just like with simplex, there's a whole bunch of heuristics that you can employ, right? And the question is, which variables do you focus on first? Do you fix ReLUs? Do you fix bound constraints? We tried playing with these back and forth approaches from start to end, from end to start, and these were not particularly successful. There are more clever heuristics for choosing which constraint to focus on first. And these are typically very similar to what I cryptically mentioned earlier, where you sort of try to measure the overall infeasibility of the problem and decide which variable is currently harming you the most, and then focus on that variable and fix that one first. So I know it's a lot of hand waving, but maybe the intuition is coming across.
Okay, thank you.
Okay, another question in the chat. Given how the phases are more or less independent, could we view ReLUplex as an SMT combined theory, combining LP with ReLUs? Yes, so this is precisely how we phrased it in the paper. So you can think about it as if the algorithm was independently solving the weighted sums and the ReLUs. And this is indeed what I showed you in the example. Each step was dedicated to either fixing a weighted sum that was currently violated, right, a bound constraint that was violated, or fixing a ReLU that was currently violated. So you can indeed treat this like a modular device that one part of it solves the linear constraints and another the ReLU constraints. So definitely.
Do you always have to flip-flop between the two stages, sort of one then the other?
So this is again heuristics, right? So what we did in the original ReLUplex was first take care of the linear constraints, which are generally easier to solve, then fix any ReLU constraints, and then if you broke again linear constraints, then go back and fix them and repeat. Any other questions? Okay. So what are some of the interesting properties of ReLUplex? So much like simplex, ReLUplex is sound and complete again with a little star. Okay, so soundness means that if it says sat, your problem is sat. If it says unsat, your problem is unsat. So much so good. Completeness, again, which really here means termination, right? We're guaranteed that the algorithm will terminate if you again do a variable selection strategy, use a variable selection strategy that guarantees termination for the linear constraints, and if you occasionally split. Okay, so in the example that I showed you, we didn't need to do any case splits on ReLUs, but in practice, you often do need to have case splits. You cannot ignore this completely. And if you apply a strategy that says that whenever you have linear constraints, you use a strategy that eventually solves them, much like simplex. And if you will always eventually split again, that you're never in an infinite sequence of steps in which you never split, then you are guaranteed that the thing will terminate. Okay, so you cannot avoid splitting altogether, but you can do that as lazily as you want, as long as you eventually split. If you see that you cannot solve the problem, you have to do a split. So this is the little star. If you do this, then the algorithm terminates. Okay. So what are some of the enhancements that you can do, right? So we already saw one aspect of the algorithm, which is the lazy splitting, right? So instead of splitting on the ReLUs, we try to postpone that as much as possible. And the strategy that we used in the original ReLUplex paper was to first fix any bound violations. So first the linear constraints. And once all of these variables are within bounds, only then address any broken ReLU constraints. And if you detect that a ReLU is repeatedly broken, then you split on it. Right, so suppose you solved all your linear constraints and you see that ReLU number 7 is currently violated. So you fix it. And then a few iterations later, it again becomes violated. And then the third time that it becomes violated, you say, okay, ReLU number 7, we've had enough, right? We're going to split on you. You are obviously problematic. So then you do a split on that ReLU. This is how we did it in the original ReLUplex paper. There are even more advanced strategies for doing that. But really, as long as you do this lazily, then you gain a lot in runtime. So in the original ReLUplex paper, we saw that the splitting fraction was about 20%, right? So in general, as a rule of thumb, at least for the examples that we considered, you only had to split on about 20% of the ReLUs, which is quite significant because remember, the number of splits affects you exponentially. So instead of doing 2 to the power of 300, we only had to do, say, 2 to the power of 60 or even less, which is a very significant reduction in runtime. And this is precisely what moves the problem from infeasible to feasible on a reasonable computer. So it turns out that you can reduce the splitting even further right? Even beyond this lazy approach. And the key thing that people are doing in order to reduce splitting is called bound tightening. So in simplex and also in other algorithms, when you verify the neural network, you repeatedly encounter equations. Right? In simplex, we saw that in every iteration, you manipulate an equation. So you see many equations. And you can actually use these equations in order to perform bound tightening and reduce the search space that you need to explore. So for example, suppose you run into the equation x equals y plus z. And currently you have these lower bounds. Okay, you know that x is at least -2 and that y and z are each at least 1. This is the state that you have right now. And then you bump into this equation. So anybody volunteers to say, what can you learn? Can you derive any tighter bounds here? Okay, you're all very shy. Okay. So Matthew writes that you can indeed derive that x is greater than 2 or greater or equal, right? Because it's pretty straightforward. If y and z are each never less than 1, then x can never be less than 2. And so you can derive the tighter bound that x is at least 2. So you can actually go to your table and update this in your state. And why is this useful to us? Well, actually, this is super useful because if x turns out to be part of a ReLU pair, which many of the variables are in a verification problem, then you are guaranteed that this ReLU can never be inactive. Right? It doesn't matter if x is the input or the output of the ReLU. If it's never less than 2, then that ReLU is never going to be inactive. So you can just throw away the ReLU constraint and replace it with the linear constraint that expresses the active phase of the ReLU. And once you do that, every ReLU constraint that you destroy like this saves you a split. So it reduces your runtime by 1/2, right, by 50%. So if you do this a lot, you can significantly curtail your search space. So this is very useful. So really, we propose this basic approach in ReLUplex, but since then there has been a lot of work dedicated to deriving tighter bounds. So there are now very clever strategies and techniques for taking the state of simplex, the equations and the bounds, and sort of propagating tighter bounds to many of your variables in a way that hopefully saves you the need to do a lot of splitting. So this is bound tightening, very crucial, very important. Okay, so we said this now, so no problem. Another thing that you really want to be doing is called non-chronological backtracking or backjumping. So this is a technique that is very common in SMT solving and SAT solving. So in a very naive way, what you do when you traverse the search tree is whenever you hit a dead end, right, whenever you get unsat, you backtrack and you flip your last decision and you go to a different branch of the search tree. Backjumping is a more clever technique that says that sometimes you can jump to a much earlier part of your search tree. Really, you can throw away a large portion of your search tree without exploring it at all. So here's an example, right? So normally, so this is a very simple search tree where you have only 2 ReLUs. So normally we would start with one branch. So maybe first we guess that the first ReLU is active, which is this branch. And then we guess that the second ReLU is active. And then we hit unsat. So normally what we would do here is we would flip our last decision. So the last decision was that the second ReLU is active. So we would go to another branch here that says that the second ReLU is inactive. What backjumping does for you, it says in some cases, when you hit this dead end, you can say, look, I know I should probably continue to this next leaf here, but I can in fact deduce that the reason that I got unsat is already because I made this guess here. Right, so it really doesn't matter. So it's true that I guessed that the second ReLU is active, but it didn't play a part in me saying unsat. And so even if I had guessed instead that the second ReLU should be inactive, this would not have changed my result. And once I determine this, then I don't need to go to this other leaf here and I can back jump. I can jump back 2 levels instead of just 1 level and continue from there and go to this part of the search tree. So I'm not explaining how it's done. Okay, how can you say that only some of your guesses played a role in your declaration that this branch is unsat? But this is something that we know how to do. It's a common strategy in SAT and SMT solvers, and you can apply it to this setting also. And in this case, it saved us 25% of the leaves, right? Instead of 4 leaves, we only needed to cover 3. So it can really save you a lot of the branching that you need to do. So very useful. Any other questions on back jumping or on bound derivation? Okay. So some additional enhancements that we added after the original ReluPlex paper. So the follow-up project to ReluPlex is called Marabou. This is the active version of ReluPlex that we're currently maintaining. This is a collaboration between the Hebrew University and Stanford University and a bunch of other research groups that are contributing code. So there is a lot of engineering work to be done if you want to efficiently implement such an algorithm. Right? So for example, you want to support a lot of input formats for networks and properties. You want to have parallelism. And today you have many cores that you can harness, and you want to take the problem and break it down into components that are each solved on a separate worker. So these are all very important things that you need to think about. Network level reasoning, I won't go into, but this is a clever way to derive tighter bounds that we already mentioned, etc. So there's a lot of engineering and other enhancements that need to go into really implementing such a solver. Okay, so we talked about the simplex algorithm for solving linear programs. We then showed how it can be extended to ReluPlex, which is more useful for solving linear programs plus ReLUs, which we saw is enough to encode a neural network verification problem. And we gave some highlights as to how to efficiently implement such an algorithm. And in the last part of today's talk, I want to talk about some of the cases where we applied ReluPlex and what you could do with it. And specifically, these will be the AKS-XU example, adversarial robustness, and also some work on clustering. I see now a question in the chat. Are there strategies for reasoning about partial guesses, i.e. for leaving the phase of some ReLUs undefined? So the algorithm, the ReluPlex algorithm by definition, always tries to solve the current problem that it has, in which many of the ReLUs are undefined. Right? The sum of the phases of the ReLUs are not yet fixed. And this is something that you immediately guess. ReluPlex always reasons about partial guesses. It's very important to use a good strategy for splitting, right? Because we know that a bad strategy will make it so that you are unable to solve the problem at the intermediate nodes, and you will eventually need to get to the leaves, and then you will do a lot of work, and the algorithm will run very slowly. If your strategies are more clever, they're more useful, then you won't need to go all the way to the leaves. So ReluPlex will always try to reason about your partial assignment, about your partial phase fixture, but it's very important to have good strategies for how to split and how to curtail the search space in order to avoid a lot of the unnecessary splits. I hope that answers the question. Okay, so just to remind you what we saw yesterday, the AKS-XU system is the system for airborne collision avoidance system being developed by the FAA. And I hope you remember this little picture that shows the on-chip is our plane, the intruder is the other guy, and the system reads some sensor information, and it needs to tell the on-chip whether it should continue flying straight or whether it should turn right or left and by how much. So this is the system that was being developed by the FAA. And the app implemented it using neural networks. So yesterday I told you the story about how this came to be, but for now, just if you forgot, just assume that they want to implement them using neural networks. And there are certain properties that the FAA absolutely needs to know that are satisfied by these networks. For example, they need to know that the alerting regions are consistent. Right? So if in a region that appears to be completely clear of conflict, you cannot have turning advisories hiding somewhere inside. So the alerting regions have to be consistent. They also want to be absolutely certain that there are no unnecessary turning advisories. Right? In cases where the intruder is not a threat to us in any way, we shouldn't turn. Right? Because you might say that turning does not, it doesn't harm you. Right? If the intruder is very, very far away, you turn left or right, probably doesn't matter. But no, the FAA really wants to be sure that you don't turn when you don't need to. And the FAA also wants to very much avoid strong alerts. Right? So strong alerts, strong right and strong left are considered bad, they are considered wasteful. So they should be avoided whenever possible. And specifically, if the intruder is vertically away from us, distant from us, then we shouldn't issue these strong turning advisories. So these are some of the properties that the FAA really cares about for this system. And they know how to define these properties formally. Right? So here it's again wave flapping, but hand flapping, but the FAA knows how to mathematically define these things. So they gave us a list of 10 properties. Okay, for example, here's one of them. If the intruder is near and approaching from the left, then the network advises strong right. And they know how to formally mathematically define this, right? So here are some of the definitions. And this we were actually able to prove, right? So using the ReLUplex implementation, we took this property and we were able to show that it held for any possible input that satisfies these constraints. Okay, so this is again a very strong statement, much more than testing, because this is not just about a finite set of inputs that we sampled, but really for any input that satisfies these constraints, the property will hold. So this is one example. Another, if the vertical separation is large and the network previously told us that we need to turn left, then it will continue to do so, or it will tell us clear of conflict. So again, formally defined. And here we were actually able to find a counterexample. So when you verify a system officially, you want to prove that it is correct, but really what you want to do is to find bugs, okay? Because this looks much better for the verifier. So we were very happy to find this bug, right? So in this case, the bug is just a concrete input, an actual assignment that you can go back to the FAA with and say, look, put this into your neural network and you will see that it misbehaves. Okay, so these are the two possible outcomes of verification, either you say SAT or unsat, counterexample or property holds. So this is some of the statistics, not very important. It's available online if you want to look. Another use case that I talked about yesterday is this adversarial robustness, right? So remember, you start with an input that is correctly classified. For example, in an image recognition network, an image of a panda that is correctly classified as a panda. You add a small input perturbation. So the epsilon means each pixel is only slightly perturbed, and you overlay this on top of that, and you get the image on the right, which is still a panda to us, but now a gibbon to the neural network. So this is the problem, right? So we want to use verification to prove that this cannot happen. So the verification query that you can pose, and we also briefly mentioned this yesterday, you take a concrete point x0, a particular panda, and you say how much noise an adversary can add. So you define some delta amount of noise, and you ask, does the classification always remain the same? And so you pose this as a verification query. You say that the input entries cannot change by more than delta each, and that the output, one of the other outputs should exceed the output that signifies a panda. Okay, so yeah, well, this should be negated, right? It's currently given, this is what we want, and we will negate it for the verification. So what you can do, and this corresponds a bit to the question about optimization, you can do a binary search in order to find the optimal delta for which robustness holds. Right, so for example, here we took one of the AKSXU networks, and we took 5 input points. Right? So each row of the table is a particular input point in the entire input space of the network. And each column of the table shows you how much noise the adversary was allowed to add in L infinity norm. Right, so here the adversary can change each input entry by at most 0.1. In this column by at most 0.075, etc. Right, so these are small changes and they become larger as you move leftwards in your table. So we pose the verification query for adversarial robustness on each of these points and each of these amounts of noise, and you can see that for some points robustness is high. Right, so for example, for point number 2. The problem is unsat even if you allow the adversary a lot of noise, right? So we know in some sense that in this point the network is robust. And remember that this is true even if tomorrow the smartest adversary in the world comes along. If you only allow this adversary to change each pixel by at most 0.1, they will not succeed in fooling your neural network. Right? So this is a very formal guarantee that does not depend on the attack vector that you use. For other points, like point 1, you can see that at some point the answer flips. Right? So for small deltas, it's unsat, and then at some point it flips to sat. So this means that the optimal solution, the minimal delta for which you can find a counterexample, an adversarial attack, is somewhere between 0.05 and 0.025. And of course, if you want higher precision, you can continue the binary search until you track down the first delta up to your desired precision. Okay, so any intuition about why the time for point 1 increases as you increase the radius? I would expect it to decrease. So a very good rule of thumb is to not try and make any sense of why you think things should solve more quickly or more slowly. Okay, so intuitively you say that right, this should be easier maybe for smaller deltas, and then as you increase, at the very least you expect monotonicity, right? You don't expect it to first increase and then decrease back and then increase and decrease again. This is a very strange graph. But in practice, what verification tools do, especially SMT solver and SMT-based solvers, is they have their own internal strategy of traversing the search space. And once you change the search space, even by a tiny bit, the whole search sequence can change, and then you can get different runtimes. So you can spend many fun hours trying to gain some intuition as why things are solving quickly and why others are solving slowly. In my experience, this is probably a waste of time. What are the implications to robustness, correctness, throughput when using fixed point arithmetic versus floating point? So an excellent question. So the ReLUplex algorithm, as I defined it earlier, and also the simplex algorithm, when you think about the algorithms theoretically, then you're only talking about precise arithmetic. And then the algorithms are completely sound and they're correct and everything is great. But when you really want to implement these algorithms, typically you use floating point arithmetic, because floating point arithmetic is orders of magnitude faster than precise arithmetic. And once you use floating point arithmetic, you get all sorts of funny side effects, right? You can take a value of x, multiply it by 2, divide it by 2, and then you don't get back to your original x. And what this will do is it can theoretically change results from SAT to unsat and vice versa. So it can mess with your soundness. So when you try to implement an algorithm that uses this kind of arithmetic floating point, you have to be very, very careful, and you have to double check every computation and be very careful about the side effects that can potentially harm your soundness. So even if you're very careful and you're monitoring your numerical stability all the time and you're sure that you're not doing any mistakes, it is possible that you will return a wrong answer. So here the answer splits in two. So if you want to return a SAT answer, then you return a counterexample. You have a concrete assignment. Then you can double check everything very easily. Just take your concrete assignment, put it into your neural network, evaluate, and say that this is truly a counterexample. So for the SAT case, this is easy. For unsat, it's trickier because the verification engine tells you, well, I don't have a counterexample. And you don't know if this is really, this is because there really isn't a counterexample or because there was some numerical issue. So what we can do in this case, and this is actually an active field of research that we are working on right now in Marabou, is to produce a proof certificate. Okay, so what we want to return when we say unsat is a very small certificate that says, look, the answer is unsat because we did this and this and this. And it will be a very short recipe that will explain to you how we deduced that the problem is unsat. And we will double check. And for these recipes, you can check that there are no numerical stability issues in them. And then you would be satisfied that the answer is unsat and you would trust the verifier. So this is common practice in SMT solvers. When they say unsat, they want to produce a proof certificate. As far as I know, this has not been done yet in neural networks, and we're actually working on it right now. Any other questions? No, okay. So the usual question that I get when I show this slide is, okay, well, that's very nice. You selected 5 points in the input space, but what does it mean about the overall robustness? Right? Maybe for other points, the robustness is weaker. How can you deduce anything? So this is one issue with what I just showed you. Okay, I will get back to it in a second. I forgot my slide ordering. So really, what we saw here is that you can use verification to measure the robustness of a neural network, but really you can do some other stuff as well. Specifically in the deep learning community, they are proposing attacks and defenses all the time. So attacks are ways to find adversarial examples, and defenses are ways to change your neural network so that it becomes more robust. So it turns out that you can use verification to assess these things. So for example, suppose I have somebody that comes along and they say, look, I have this amazing attack. Please evaluate it for me. What I can do is pick a point X, use verification to find the optimal delta. So the minimal amount of perturbation that I need to add in order to fool the neural network. Then use the attack to find delta prime, so the delta that the attack can find. And then ask myself, how close is delta to delta prime? If delta prime is very close to delta, and I will of course run many experiments, if delta prime is very close to delta, then I can say, look, your attack is pretty good. It finds perturbations that are very close to the optimal. And if delta prime is much larger than delta, then I will say, well, maybe you should still improve this attack right before you try to use it. And for example, we took one of these attacks, the Carlini-Wagner attack on a small MNIST network, and we saw that on average, the deltas that were optimal were only 6% smaller than the deltas returned by the attack. So in some sense, the attack was pretty good, right? It was never very far off, well, on average, it was not very far off from the optimal ground truth attack that you could find. So this is for assessing attacks, but you can do the same for defenses, right? So suppose somebody comes along and they say, look, I have this amazing defense, please assess it for me. No problem. We take the original network N, we train the hardened network N bar using the defense technique. We pick a point and we compare the optimal delta that we find using verification before and after the hardening. So we compute once delta for the original network and once for the hardened network N bar. And if we see that the deltas have become much larger after the hardening, right, more noise is required, then we say that the hardening was a success. So we evaluated this on a defense by Alexander Madry and his colleagues on a small MNIST network. And on average, we saw that the hardened deltas were about 4 times larger, right? So 423% larger. So this we thought was a very nice result, right? So they pushed back all the adversarial examples by a factor of 4, even more than 4, which is very nice. However, we detected that in some cases, the defense actually made things worse, right? So on average, it was good. The average attack now could only find deltas that were significantly larger, but in some cases, the defense made things worse, and for some points, the deltas actually became smaller. So interesting findings, I think, and we think that verification can really help you evaluate these kinds of attacks and defenses. Another question, how much faith can you put in such assessments if they only involve, say, one network and one point? So this is an excellent question for my next topic, but really everything in machine learning is statistical, right? So if you have a network that has millions of neurons, right, and you want to harden it, you cannot verify that network because it has after the hardening, because it has too many nodes, too many neurons. So what you can do as a proxy, right? You take a smaller network, you apply the same hardening technique and use verification to measure. So of course, you're not guaranteed here that it will really, the results will really carry over, but we think that it provides you with some guarantee that you cannot otherwise get. And there's also global robustness, which I will talk about in a second. So even if M and N are small, so sure, I mean, you are not guaranteed, if you only look at specific points in the input space, you are not guaranteed that this will carry over to the entire input space. But let me continue to my next slides, and I hope it will answer some of the questions. So just like Wen was asking in the chat, this kind of querying is problematic because you only focus on particular points, and you are not guaranteed that any result that you get will carry over to the remaining points of your input space. So another issue, apart from this carryover question, what is an acceptable delta? Right, so we can have some points in which delta should be low, right? You expect low robustness, and other points where you expect high robustness. So you need to somehow distinguish between these things. And these are all very good questions. So for example, if I take the FAA network and I look at 2 points, X1 and X2, X1 appears to be deep within the weak right region. So I expect a high level of robustness. I expect that even if I add some noise, the result will still be a weak right. However, X2 is on the natural boundary between two labels, right? So it can be either weak right or clear of conflict. So if I allow even a small amount of noise, it's quite reasonable that it will flip it from one advisory to the other. So I need some way to solve all of these issues if I want to reason about robustness. So for this, we propose another variant called global robustness. And the idea in global robustness is not to check that the classification remains the same, but instead to look at the confidence levels that the network assigns to each label. So what we will want to say is that if we have 2 points, X1 and X2, and these 2 points are nearby, so the distance is no more than some delta, then I look not at the classification of these points, but for example, at the confidence levels that they both assign to say clear of conflict, the advisory. So I will not require that necessarily they say clear of conflict or that they both agree that it is a clear of conflict or not a clear of conflict. I will instead only require that the confidence levels that each of them assigns to clear of conflict are similar. And this, I claim, will solve this issue, right? Because even if I'm at point X2, then I say, okay, I'm not sure if this is a weak right or a clear of conflict, But I do expect that slight perturbations will not change the point into something that is very clearly clear of conflict. The confidence levels should still be similar to what they were before the perturbation. So this, I claim, answers the problem of points that are on the natural boundaries between labels. So this is one half of the problem. And because you ask this for all x1 and x2, right? I didn't previously. I would fix one of the points. I would say I have an x0 and I allow a small perturbation around it. Now I say for all x1 and for all x2, so I can immediately pose a verification query that captures a continuous part of the input space, or even the entire input space if I want, in a single query. So if you get an unsat answer on this, right, if you can prove this, this is a much stronger statement. And this, I think, answers some of Wen's question about how you can trust that something is correct for the entire input space, or at least portions thereof. Right, so this is global robustness. And this also, you can take this, you can pose this as a verification query. It meets all of our requirements, no problem. The only problem is that this is significantly slower to solve. Okay, these queries tend to be computationally heavier and they are slower to solve. So we can pose them. And as verification technology continues to improve, we should be able to prove them for increasingly larger networks. One question that is still unanswered, even if you switch to this global robustness thing, is how do you define delta and epsilon? Okay, what is an acceptable delta? What is an acceptable epsilon for you? And this is not a very easy question to answer, right? How much noise is acceptable? I don't know, do you? So there are actually even ways to try and adjust these things automatically. So I will briefly mention one of them. So this is a project called DeepSafe, which we published a few years ago. And the idea is to use clustering in order to identify regions where the network should be consistent, or in other words, to automatically select epsilon and delta. Okay, so you can apply clustering, for example, to the training set, or really to any set of points where you know what the labels should be. And then when you apply clustering, what you get is a centroid. You really identify a center point of this region that is all classified the same way, and a radius, which defines a sub-portion of the input space that should have consistent classification. Right, so for example, if you have this is a network that distinguishes between stars and circles, and the stars and circles that you see are all part of the training set. So these are points that you know are guaranteed, that you know that the circles are really circles and the stars are really stars. What a clustering algorithm will do for you is it will say, look, I see that there is a cluster of circles here, and the centroid is probably somewhere here, and this is the radius. So I say that this entire subregion should all be made of circles. And so this is a verification query that you can then pose. Likewise for stars, you identify portions of the input space that should all be classified as stars. And this lets you automatically discover these verification queries that you can then ask. And then you can pose the global robustness query with, or a local robustness query with the epsilon and delta that you get. So this is another step towards automation. And we know that it's really important. It's difficult to get good specifications, and you want this to be as automated as possible. Any questions on global robustness or clustering? No. Okay. So let's wrap up this part of the slides. So we see that software that is generated by machine learning is really becoming widespread. We know that certifying the software is a new and exciting challenge. Well, it's definitely new, and I definitely find it exciting. And I think, and I know that other folks in the community agree, that verification can play a key role in addressing this concern. Maybe it won't be the only solution, maybe it will be part of a tool suite, but I expect that it will play a significant part in solving this issue. And the main questions that we need to answer is, first, how do we verify? We said that the problem is computationally heavy. How do we solve it efficiently? And the other question is, what do we verify? Even if we have this huge hammer, if we can solve any verification problem that we want, what do we ask? What do we verify? So these are the two main questions. So in the how area, we saw that there are roughly two categories of tools. There is the sound and complete approaches. These approaches solve an NP-complete problem, so they tend to be slower. They are usually based on case splitting, which we discussed thoroughly. And they can be improved with tighter bound derivation, splitting heuristics, and local optimization steps that we touched on briefly in today's talk. The other approach in the how section, how do you verify, is to trade completeness for scalability. You say, okay, I won't be able to solve all the problems, but some of the problems that I can solve, I will solve more quickly. So we talked a little bit about discretization and exhaustive search. There are correct by construction networks that you can think of. And orthogonally, there are also abstraction techniques that we will talk about later in the week. And I won't say anything more about that right now. So that was in the how section. How do you verify? The other question is the what, right? What do you verify? So one approach is to use domain-specific properties, right? So for example, ACAS-XU. The expert comes and they say, look, this is our network. It does airborne collision avoidance. This is what we want to verify. So your properties are highly domain-specific. This is good, but it requires a human input, right? It requires a human in the loop, which is a known issue in verification. It's difficult to get the engineers to write the specifications for you. So this is one thing that you can do. And the other is what we call general properties or universal properties. So for example, adversarial robustness. It doesn't matter what my network does. Is it a network that does image recognition or audio recognition or a network that flies aircraft? It doesn't matter. I want it to be adversarially robust. I never want small changes to cause my neural network to misbehave. So this is a universal property. We always want it to hold. Right, so there are a bunch of these that I will talk about later. Well, I thought I would talk about today, but maybe only tomorrow. Right, so we know a few other approaches, a few other properties that we consider to be universal. So some of the work that we are currently doing in ReluPlex/Marabou, so scalability. Right, so we're always working hard on improving scalability. So some of the things that we talked about earlier is that the linear solving and the ReLU solving are currently, at least in the example that I showed you, are currently done separately. And we're trying to fuse them together in order to get better performance. So maybe perhaps in a single update or pivot step, you will be able to solve both kinds of constraints, not just one and then the other, and then flip-flop between the two. And we also talked about proof certificates, which are a way for gaining confidence that your ansat results are indeed ansat and that there are no numerical stability issues hiding inside. So these are also things that we are working on. Then there's more expressiveness, right? So specifically non-linear, non-piecewise linear activation functions, so sigmoids and hyperbolic tangents. The ReLUplex and really all splitting-based approaches are very suitable for piecewise linear constraints, but you want to also solve non-piecewise linear constraints. So these are things that we are working on, and of course, additional case studies. So I think maybe the most sorely needed thing in the community is more benchmarks. So real industrial benchmarks from folks that have real networks and they want to verify real properties on them. So this is something that we are very actively looking for. Actually, there's a collaboration now between my group and a group at Heriot-Watt University, Katya's group, that this is precisely what we're looking at right now. So that's it. I'd be happy to answer any more questions on this part of the slides. I see there's actually a question in the chat. Do you know of any relevant material about distribution-based input noise? So instead of having X in a certain range, if X is sampled from Gaussian distribution. So there is a branch of probabilistic verification where you can ask these kind of queries where you want to gain a certain level of confidence based on a certain distribution or certain probability. I know of these kind of things for traditional systems. I'm not aware of anybody that has considered them for neural networks, but this is a very interesting research question. I think this will be particularly suitable for cases where you are concerned about, for example, adversarial examples, but not because you fear a malicious adversary, but because you are concerned about just the randomness of things and statistical distributions. So yeah, so this is interesting. Okay, so Matthew says that there is a paper from DeepMind. So I think the papers from DeepMind usually work on correct by construction networks, but perhaps they have also studied this topic. So I was going to start my next set of slides, but it is almost time to finish. So I think it would be better to just save them for tomorrow. But really, if anybody has any other questions, go ahead. No. Okay. So let's wrap it up and see you same time tomorrow.
Let us thank the speaker. Thank you. Well, if there are any further questions, do let us know. Otherwise, the session tomorrow is the same time, 10 a.m., I think.
Yeah.
Be on the lookout for any emails, as we may need to change the Zoom link. If we do, you will get an email. Otherwise, check in on Zulip. That is all for now.
Thank you.
Thank you all.